Can you believe it? Scientists have analyzed the data from the Webb telescope and found that we might be living inside a black hole of a larger universe. These findings not only challenge the scientific textbooks, but also prompt a re-evaluation of Einstein's theories, from the origin of the universe inside a black hole, to the mirror particles behind dark matter, and next, we'll take you through the ultimate puzzles that overturn human understanding. Since the launch of the James Webb Space Telescope, it has observed those mature primordial galaxies, which, in the context of the universe at that time, appear to be very old, large, and well-structured, completely mismatched with what galaxies should look like during that period. It's like being in a kindergarten, and suddenly seeing a group of college students in class. Isn't that perplexing? So their existence directly challenges the existing theories of cosmic evolution. However, is it possible that the issue does not lie with the model itself, but rather, we are standing in the wrong position? For example, what if we try a different cosmic perspective? What if the James Webb Telescope is actually guiding us to understand a completely new reality? This crucial aspect has to be explained by redshift. Redshift is the stretching of light due to the expansion of the universe. The farther away a galaxy is, the more its light is stretched. Astronomers use this to measure how far away galaxies are and how old they are. This time, the James Webb Space Telescope is really giving it its all. It's almost seen the universe as it was 13.5 billion years ago. At that time, the universe was just 13.8 billion years old. According to the standard model, galaxies at this stage should be small and irregularly shaped. But what the James Webb Telescope has observed are all large and regular galaxies, all at once. Scientists can't sit still anymore. They are rethinking their understanding of the universe. Even more outrageous things are yet to come. After the James Webb Space Telescope's Advanced Deep Field Survey observed 263 galaxies, it found their motion remarkably coordinated. This suggests that our universe might be residing inside some black hole. A new study analyzing the James Webb Space Telescope observations of the early universe reveal a strange fact. Most galaxies are rotating in the same direction. The lines formed by the curved tips of those galaxies' spiral arms helped us identify their direction of rotation. According to logic, if the universe were truly random, the rotation directions of galaxies should be evenly split between two directions. However, the situation discovered by the researchers does not align at all with existing cosmological models. It might just be suggesting our universe might actually be inside a black hole. We need to figure this out. We first need to take a look at what a black hole is. When matter collapses under the force of gravity to form a black hole, it creates an event horizon. It's a boundary, and once you cross it, nothing can escape, not even light. For an outside observer, an object that crosses this boundary is completely finished. But what lies inside the event horizon is anyone's guess. At this moment, black hole cosmology, also known as Schwarzschild cosmology, it was time for it to take the stage. It says that the universe we can see might just be the inside of a black hole in a larger universe. This brings us back to the time of the Big Bang. The standard model states that the universe began from a singularity of infinite density, just like the center of a black hole. If our universe is really a black hole in a larger universe, then the Big Bang was not an expansion of matter into empty space, but rather a collapse of matter into a black hole, which then creates a new universe inside. In this way, every black hole in our universe could be a gateway to a new universe. This could also explain why the fundamental constants of our universe seem finely tuned, suitable for life to exist. Because black holes that can create stable universes could allow for long-lasting existence, and then give rise to new universes. Scientists are pondering that this theory might unlock many mysteries of the universe. For example, black holes have a particularly high entropy, which corresponds to the immense amount of information in our universe. For example, in the extended theories of general relativity, such as the Einstein-Cartan gravity theory, I mentioned the twisting of spacetime. Twisting takes into account the effect of particle spin on spacetime curvature. Some theories suggest that, at particularly high densities, this kind of spacetime distortion can generate repulsive forces. In simple terms, it prevents the emergence of singularities. If that's the case, black holes could undergo a big bounce. The core rebounds and then expands outward. It might even create a new universe. Scientists also say that, if there is a rapid rebound after the big bounce, that could mark the beginning of our universe's expansion. In other words, the Big Bang. Therefore, this is not a singularity exploding out of nowhere, but rather reborn from the core of a black hole in a larger universe. If this theory holds water, it would fundamentally overturn our understanding of the origin of the universe. The cycle of the universe would become a continuous, self-replicating process. Additionally, the universe might have a preferred axis. When observing the large-scale structure of the universe, it has been found that the distribution and motion of galaxies seem to be somewhat aligned. It's not completely random. This so-called cosmic anisotropy challenges the widely accepted cosmological principles. That is, the universe should be isotropic and homogeneous on large scales. If the universe truly has a preferred direction, it may suggest that there are unknown physical laws at play. It could be related to how our universe formed within black holes, or it could be connected to the interactions of fundamental forces on large scales. However, the matter of primordial massive galaxies has also raised questions about the evolution of the universe. But we should also be cautious. Perhaps there are more ordinary explanations. Maybe some previous measurements of our universe were incorrect. For example, the rotation speed of the Milky Way, or the universe might be older than we think. Regardless, the universe is turning out to be even more mysterious than we once thought. The fact that galaxies don't rotate uniformly, this is likely to prompt astrophysicists to re-examine their understanding of the universe. Do you think our universe is inside a black hole? Although this idea is quite appealing, a recent research paper suggests that there is a mirror universe. Time runs backward in there. Have you heard of Occam's razor? In scientific reasoning, this is a very useful principle. To give an example, if astronomers see unexplained light on other planets, if they directly say that it's aliens, that would be too hasty. Occam's razor reminds us to first consider simple explanations, such as atmospheric conditions or natural phenomena of the planet itself. So why mention the Occam's razor here? Because many inflation models suggest that the rapid expansion of the universe in its early stages would generate long-wavelength gravitational waves. These are ripples in spacetime. If we could detect these waves, it would add significant weight to inflation theory. Scientists have indeed detected gravitational waves now, but those are all from events like black hole mergers or neutron-star collisions. Even though we've gone through a heck of a lot to search for it, but we just can't find any trace of primordial gravitational waves. Each new experiment rules out more inflation models. While inflation theory does explain why the universe appears so homogeneous on large scales, it also brings about several new problems. For example, what kind of energy field is driving the expansion? Does inflation require the universe to have very specific initial conditions at the start? But why do these conditions arise? No one can say for sure. Some inflation models even suggest an infinite bubble universe. This leads to a host of philosophical and scientific questions about whether they can be tested, and the nature of physical reality. So, if we set aside the Occam's razor factor, it means assuming there is no simpler explanation. This matter falls on Neil Turok, the chair of theoretical physics at Higgs, and his colleague Latham Boyle. They developed a new theoretical model, trying to do this without relying on traditional inflation theory or string theory, to solve fundamental cosmological problems. If we use Einstein's general relativity and known physical laws to reverse the time of the universe, it ultimately shrinks to a point, the initial singularity. To understand the universe's dense and hot state at the beginning of the Big Bang, theorists like Nobel laureate Roger Penrose found that there is a key symmetry in the laws of light and massless particles, called conformal symmetry. What this thing means is, light and massless particles are not squeezed like other matter during the Big Bang. They can pass directly through those extreme environments. You can imagine the universe as a piece of elastic rubber. There is a picture on it. If you stretch or squeeze this rubber, the size of the picture will change, but the shape will remain the same. Conformal symmetry means that, regardless of how the universe scales, its structure remains unchanged. This might mean that the uniformity of the universe naturally emerges from this symmetry, rather than being shaped by an explosive event like expansion. They propose that the initial singularity is not a one-way starting point, but like a mirror in time, one side moves forward in time, while the other side moves backward in time. It's like the universe is looking in a mirror. The Big Bang acts as a mirror to every physical process. It reflects spacetime and particles in reverse. This follows CPT symmetry. It represents a fundamental balance in nature. You can imagine the universe as a grand stage. Particles are performing a play. In this play, there are three rules: charge, parity, and time. Charge is like swapping matter and antimatter. Parity is like flipping the scene in a mirror. Time is like playing the play in reverse. If you reverse all three at the same time, the laws of physics remain unchanged. The universe continues to operate as usual. It's like a well-rehearsed performance. No matter how you twist things, there won't be any mishaps. However, in our universe, there are more particles than antiparticles. Time also only moves in one direction. This seems to break CPT symmetry. The idea of a mirror universe comes to restore this symmetry. It is said that our universe has a mirror counterpart. In there, time flows backward, and antiparticles have the upper hand. This parallel universe may not necessarily be a real place. It might just be a mathematical tool, used to explain the symmetry during the origin of the universe. Their theory also involves dark matter. Neutrinos are a type of light particle. They travel at speeds close to the speed of light. The spin direction is left-hand. However, it is predicted that stable heavy right-handed neutrinos could be candidates for dark matter, because they are only affected by gravity. Turok and Boyle calculated using the mirror hypothesis that these right-handed neutrinos could indeed explain dark matter K. This theory also states that if dark matter is composed of heavy right-handed neutrinos, then among the three known light neutrinos, at least one must have a mass of 0. This prediction is being validated through the study of how galaxies and other cosmic structures are laid out in space, observing how matter accumulates in the universe. This might lead to clues about neutrino mass. Thus, we can assess the reliability of this dark matter theory. Scientists have also investigated why the universe appears flat and uniform on a large scale. They use entropy to explain this. Entropy describes the likelihood of a certain configuration. They discovered that a flat and rapidly expanding universe, with a slight positive acceleration, is the most likely state to occur. Additionally, they pointed out that the density variations usually thought to be related to expansion can actually be explained using quantum fields. However, this new theory still needs to undergo more tests to establish itself scientifically. Turok wrote in the Physical Review letters when publishing the team's findings to view the Big Bang as a mirror, which can effectively explain the features of the universe that seem to conflict with physical laws. But Turok also noted that, even if proven wrong, it reminds us that there may be a simpler explanation than the standard model. What does everyone think about this? Let me know in the comments.